Hello all, my name is Vishwanath Seshagiri and this is my CS584 graph data mining final project presentation on QoS violation in microservices. So let's get started. Now, what is a microservice? Microservice is an architectural style that structures an application as a collection of services that are highly maintainable and testable while being loosely composed and organized around business capabilities. This has greatly increased the performance of each of the cloud applications, and increasingly, many cloud companies are moving towards a microservice based architecture. So, just to give you a brief background, initially the applications were all structured in a monolithic fashion. That is, you had a user interface which was on top of a business layer, which was on top of a data interface, and then it had a database layer. Now, the problem with this kind of architecture is that as your application becomes more complex, it is really difficult to scale as each part of the application grows in complexity and different people work on the same code base, making it extremely difficult for coordination across multiple teams, across multiple features, and it just becomes a headache at that point. So then comes the microservice architecture, where you have you have each of these services are now composed into per microservice basis. And let's say microservice UI would be for a particular service, and you can have another UI for another set of services. And this is pretty much what happens in modern day applications, whereas if you go to Netflix, for you the UI will be different, but for your friend it would be different based on what kind of shows you watch. And let's just see an example of how the microservice application works. Now now, before we go into that, let's just kind of zero in on what's a QoS violation. Now, the traditional definition of a QoS violation is that quality of service is the description or measurement of the overall performance of a service, such as telephony or computer network, or in our case, a cloud computing service, particularly the performance seen by the users of the network. So, how do the users of that particular network view the performance? And this can be partly attributed to how people experience different platforms. For example, if a YouTube video does not load within the 10 seconds of you opening it, you're just going to close your application and leave, and that is going to affect the end user retention on a platform, and the revenue and all of that. So basically, quality of service is the most important metric for any user on a given platform. Now, let's just see it on an example microservice, how quality of service works. So when you have an initial request coming, it's then routed to service 1, 2, and 3. And this can be anything like, your service 1 can be ad, service 2 can be your actual video, and service 3 can be your account details of what all you have watched before and things like that. And all of this is then sent to service 4, which then composes this entire web page into a single web page, and then like puts it to a cache from where the the request then backtracks these services and reaches the end user. So now what happens in this is that there is an error in service 2, and suddenly service 2 for some reason is taking way longer than what it should. Now service 2's the reason for taking longer can be anything from the CPU maxing out to too many requests in the queue, or just normal latency issues. And then this causes service 4 to take longer than what it usually does, because it's dependent on service 1, 2, and 3 for proper functioning. And then service 5 also bugs out. So just a small bug in service 2, for whatever be the reason, causes the entire network or the entire graph to get get buggy and affecting the end user performance. Now, for my use case, I make use of something called the disturbance microservices, which is a microservice suite of three major architectures, which was published at ASP+ 19, and I chose the social network application out of the three architectures which were available. Now, each of these service in a micro in social network is written in C++ and is present inside a separate Docker container, and the communication between these services happens via remote procedural calls, or RPC, which is written in Apache Thrift. And it basically contains all the major functionalities which you expect out of a social network application, such as posting text, uploading images, and seeing other people's posts and things like that. So if you want more details about the microservices, I suggest you go and read the ASP+ 19 paper for the full version, or even my project report for a concise summary. Now, the existing works in this field, one was called Seer, which was published at ASP+ 19 by the same group which gave us the disturbance microservice. So, what it does is it made use of the average queue depth at each service, which is the outstanding request at each service, and then they manually define a critical path and say, and then they have a very complex network where you have a CNN followed by an LSTM followed by a softmax, and this was trained to identify QoS violations. And the input to this network was basically the queue depth of each service. Now, another work was published at MLSys 20, which was called Sage, and they basically, it's a very short paper, but what they did was they trained a lightweight GVAE for each microservice and then used a causal Bayesian network for mapping the microservice structure. And they use multiple nodes like latency node, metric node, and latent variables for mapping this the CBN, and it did lead to decent results. Now, another work which was published at OSDI 20 was called Firm, and what Firm did was it used SVM for detecting and localizing the SLO violations, saying, "Hey, this is the node which is most likely to bug out, and probably you should give more care for it." And then they used a reinforcement learning approach for mitigating these SLOs, saying if a particular violation occurred in this node at this particular time, this is probably the most po- most possible reason for its occurrence. Now, based on all of this work, what I have done is I have first defined what is a QoS, and then I have used a causal Bayesian network for identifying the critical paths, and then I collect these traces and I construct a graph, and then I train it on a network. So let's just get started. So defining QoS was that the previous works basically did not define what a QoS means. They basically just said QoS is violated, but without really giving what is a QoS. And we base our QoS on the criteria which is provided by major cloud providers such as Google, Amazon, Azure, and we flag a QoS violation if the time taken to serve a request is greater than that of the time taken to serve 95% of requests. It might be confusing, but stay with me for a second. Now, instead of defining it at a per application basis, I basically defined it on a per service level, which makes it kind of easier to track, and you will know what I mean in a minute. So, for example, if there are 100 requests per second to an application and 95% of the requests are served within 3 seconds, it means that any request which takes more than 3 seconds is said to be causing a QoS violation. So that is what I meant earlier by saying a request is served in less than in a time less than that of 95% of requests. Now, to put things in perspective, for example, the compose post here takes all of this time to execute, and all I care about is the 95th, more than the 95% of the requests. So these are the requests which are violating SLO. Now, all of these things, which is your Mongo user, Redis get, all of these are pretty much database or cache operations, and they hardly ever cause violations. But still, because we determine the 95% criteria, you can see that there are some violations that have occurred in all of these nodes. So now, keeping in mind the definition of QoS, let's see what a critical path is. And for that, I would like to show you the UI which I use for tracing. And the comparison of paths taken by two requests. One is your API post compose and API user timeline read, which is basically reading a user timeline and like composing a post. So if you see the user timeline request, it's basically hardly 10 services long. Like you have 1, 2, 3, 4, 5, 6, 7, and then the starting service along with the nginx server which is present. But if you take the composing the post, you can see that there are way more uh, services which are used. Like you have a compose post, you have a upload with user id, upload unique id, upload text, upload media, and all of these. And at the end, it basically needs to also be inserted into the social graph service, because that is the global graph of all the connections and the users which exist. So now, based on this, we define a critical path by using a causal Bayesian network and identifying these paths. And there are three major critical paths. One is your compose post, then reading a home timeline, which is like the reading the wall of a particular user, and reading user timelines, which is basically a profile of any user, including your own. And this basically helps in isolating the types of networks which is to be trained, and which you will get to know in a couple more slides. So then based on all of this, we train a graph. We construct a graph where each trace id becomes a node in the graph, and each service name that executes within a single request becomes a part of the same graph. And then you have this trace id which is used to group these objects, and service name is categorically encoded for each graph. Now multiple deployments and new services which happen in a microservice environment are all captured when tracing the path of a request, and you don't really have to do any extra efforts for all of those. Now, as for the neural network in itself, we use a supervised learning approach for training the network, where we use a graph convolution layer network, where we replace the the traditional convolution layer with a sage-conv layer, and it's basically four stacked conv layers followed by a top k pooling layer. The reason why we go for this particular architecture is that sage-conv layers are better at understanding the interactions between multiple nodes in a graph, and then and it also performs better on an unseen data as opposed to a traditional conv layer. And we use a top k pooling layer because multiple services in a particular graph can bug out, and we want all the services to be detected, not only the services just bugging out the maximum number of time. And the input to the GCN is a feature matrix along with the adjacency matrix. And basically, we train two kinds of networks, which is globally, which is on all the trace data. And then what we do is we locally train a network for each critical path. So the critical path, as I showed in the previous slide, are read compose, read user timeline, and read home timeline. And a separate network is trained for each of these critical paths, and another network is trained for all the data as a whole. And then the results on a global network is that you have an AUC score. So all of these are AUC scores, since we had very less number of violations which occurred, and we just wanted to capture all of that. So you have around zero point 0.6 to zero point 0.7 AUC for compose post, and slightly higher for read home timeline, and even more higher for read user timeline. And this is kind of because, as you saw in the previous few demonstrations where I showed you the critical path for compose post and read user timeline, the number of services which had to be used for compose post was way higher than what it was for a read user timeline. And this kind of causes the network to understand some things wrongly. But one important thing to note here is that the variance in minimum and maximum AUC scores for each of these networks are not the same. Like for read home timeline, the difference is around zero point 0.7, zero point 0.8. For compose post, it's actually zero point 0.1, and for read user timeline, it's around 0.15 ish. So these are not the same, and this is an important point because when I trained a network for each of the critical paths separately, there was the variance was the same. Like it was pretty much zero point 0.5 in or zero point 0.4 zero point 0.5 ish in all the cases. And as you can see, the median AUC is also higher when compared to your global network, where the median AUC was around 0.65 for composed post, and this is around 0.67 0.68. And similarly you can see the trend to be higher for each of these critical paths. However, in all of this, one of the biggest problems of training local networks is that as more functionalities occur, the critical path expands, and you now have to train a causal Bayesian network for identifying all these critical paths and then extracting the traces, which is far more complex than just using a single trace data to train all the networks. And this is where I like make an uncomfortably long pause in the all of Florence here because the presentation is done. And thanks a lot for watching it.